Everybody, my name is Hoàng Dương. Today I'm gonna talk about chapter 4.1, the moment of a force. What is a moment of a force? It is defined as the turning effect of the force about a pivot, and is the product of the force F and the perpendicular distance d from the line of action of the force to the pivot. You can refer to this picture. Moment act about a pivot in a clockwise or anti-clockwise direction. The anti-clockwise moment acts downward on the left, and the clockwise moment acts downward on the right. The quantity that tells the turning effect of a force about its pivot is its moment. The moment of a force is bigger if the force is bigger. The moment of a force is bigger if it acts further from the pivot. The moment of a force is greatest if it acts at 90 degrees to the object it acts on. Balancing a beam. A seesaw is an example of a beam, a long, rigid object that is pivoted at a point. The girl weight is making the beam tip one way. The father push is making it tip the other way. If the beam is to be balanced, the moment of the two forces must cancel each other out. So, the turning effect of the force on it must also be balanced. From this we got, if a resultant force acts on an object, it will start to move off in the direction of that resultant force. One example is the girl and the father pushing. If there is a resultant turning effect, it will start to rotate. Equilibrium. When a beam is balanced, we say that it is equilibrium. If an object is in equilibrium, the forces on it must be balanced, that means no resultant force. So, as I said before, from this picture, if the two resultant forces balance, the weight of the girl and the father push, the seesaw will balance. Here a study tip. In science and in other objects, you will often hear about things that are in equilibrium. This always means that two or more things are balanced. Everybody, this is Hoàng Dương again. Now I'm going to talk about chapter 4.2, calculating moment. To calculate a moment, you need to know two things: the distance from the pivot that the force is applied, the side of the force applied. So that means the moment is equal to the force multiplied the distance. The unit of moment. Now let us consider the unit of moment. Since the moment is a force, Newton, multiplied by a distance, meters, its unit is simply the Newton meter. Nm. There is no special name for this unit in the SI system. Study tip. If distances are given in centimeters, the unit of moment will be Newton centimeters. Take care not to mix these two different units, Nm and Ncm, in a single calculation. Example of calculating moment. The 40 Newton force is 2 meters from the pivot. So, moment of the force equals 40 multiplied by 2, and that means 80 Newton meters. Balancing moment. The seesaw is in equilibrium. The weight of the child on the left has an anti-clockwise moment, and the weights of the two children on the right have a clockwise moment. The data collected from the diagram from last slide, we can calculate this moment. Anti-clockwise moment, 500 multiplied by 2, 500 multiplied by 2. Clockwise moment, 300 multiplied by 2 plus 400 multiplied by 1. 300 by 2, 1 plus 1, and 400 by 1. That means 1000 Newton meter if we add both these things. We can see that in this situation, total clockwise moment is equal to total anti-clockwise moment. Here, the principle of moment. The idea that an object is balanced when clockwise and anti-clockwise moment are equal is known as a principle of moments. We can use this principle to find the value of an unknown force in equilibrium. From the figure, we can see 4 forces acting downwards. If this was the only force acting, this would make the seesaw accelerate downwards. Therefore, another force acts to prevent this from happening. There is an upward contact force where the seesaw sits on the pivot. As we can see from the figure from last slide, the seesaw is in equilibrium. Therefore, we can calculate the contact force acting upward of the seesaw. It must be balanced to the 4 downward force, so its value is 500 plus 200 plus 400 and plus 300. That means 4,400 Newton upwards. This force has no turning effect because it acts to the pivot. Its distance from the pivot is 0, therefore its moment is 0. Now, we have satisfied the 2 conditions that must be met if an object is in equilibrium. First one, there must be no resultant force acting on it. Secondly, total clockwise moment must be equal to total anti-clockwise moment. We can use these 2 rules to solve problems concerning the forces acting object in equilibrium.
In Chapter 4.3, we will study about stability and center of mass. Stability. First one is about stability. Now, as you can see here, these are 3 glasses, and now we go to each of them. The first one is when the glass is upright. Its weight acts downwards, and its contact force of the contact force of the table acts upwards. So the glass is equilibrium. As you can see here, the glass is tilted slightly to the right, and the forces are no longer in line. So the line the glass weight is to the left of the base of the glass pivot, so it has a anti-clockwise moment. So therefore, the glass will tip to its upright position. And in the last glass, as you can see, the glass is tipped further away, so its weight acts to the right of the pivot and has a clockwise moment. Therefore, the glass will tip right over, and therefore the glass is unstable. Now we'll go to the center of mass. Some centers of mass, sometimes known as center of gravity. It is the point at which the mass of an object can be considered to be concentrated. For an object to be stable, it should have a low center of mass and a wide place. Now we'll study how to find the center of mass. So a meter rule balances at its midpoint, so that is where its center of mass must lie. For example, we will find the center of mass of this irregular shaped object. So if it's free to move, it hangs with its center of mass below the point of suspension because its weight pulls it round until the weight and the contact force and at the pin are lined up, and there is no more moment about the pin. So the plumb line is used to mark a vertical line below the pin, and the center of mass must lie on this line. And we should repeat for other 2 pinholes, and we will have 3 lines. We might have 3 lines on the card, and the center of mass must lie on all of them. And the center of mass will be the intersection of 3 lines.